Okay, today we're going to talk about enlargements. And we're going to start with enlargements, then we'll do rotations, translations, and we'll begin composite transformations. So enlargements are a horizontal and vertical stretch. So we get the matrix K00K as opposed to K001 or 100K. So it's now in both places. And this will stretch it equally in both directions. And it will have a scale factor of K. Again, this is in your formula packet. So if we want to transform this point, we must left multiply by the transformation matrix. Always left multiply. Two, bottom one, oh, two. Row two, column one is 4. And yes, that is twice as far away as the original. So doing this triangle, and then it's going to ask us something about the area. So again, we're doubling the size. A is 1, 1, B is 3, 2, C is 2, 1. 2 times 1 is, so we'll just put it over here. 2 times 1 is 2 plus 0 times 1. 0 times 2 is 2, 2. 2 times 3 is 6 plus 0 times 2 is 6, 4. The nice part about these zeros is I'm really only having to multiply one of them when I do this. So the new points become here, 6, 4, B prime. This is A prime. I need to get rid of a B prime. B prime, 4, 2, C prime. This triangle is definitely twice as large on each dimension. But something to note, area-wise, area of the triangle, base of 1, height of 1, 1/2 base times height leaves us at 1/2. Over here now, 1/2 base times height leaves us at 1/2 times 2 times 2 leaves us at 2. Notice that is 4 times the area. My scale factor was 2. My area transform, the area of my transformed figure has 2 squared times the area because it's essentially 2 in both x and y dimensions. So scale factors always must be multiplied by how the dimensions are multiplied. Okay, rotations. So international mindedness. This guy named Escher was a Dutch graphic artist who used mathematical concepts in his art, such as his art included impossible objects, ideas of infinity, symmetry, transformations, tessellations, and hyperbolic geometry. He interacted with famous mathematicians of his time like Polya, Penrose, and Coxeter. Although he believed that he did not have any mathematical talent, his artwork was based on mathematics and has often inspired mathematicians. Moreover, it was admired by the general public. So he might not have had certain mathematical talent, but he must have had some. because he was able to use these math things. The diagram shows the image created using techniques like those by Escher, and his rotational symmetry uses various transformations. And you can think about how could you create this image using computer graphics. And these matrix transformations become really useful in computer graphics. So rotations use the following transformation, actually. I'm going to show it here. This is an anti-clockwise or angles going this way, just like they do in trig. Cosine theta, negative sine theta, cosine theta is our transformation matrix. So no matter what the theta is, we can just multiply by this. So write down the matrix that represents a rotation of pi over 3 anti-clockwise. And I don't really want to leave it with these cosines and sines in here. I would like to simplify those. The cosine of pi over 3 is 1/2. The sine is square root of 3 over 2. And so my transformation matrix T is that. I mean, when you're putting into a calculator, it doesn't really matter that much, but it's sometimes nice to just get rid of the sines and cosines. It's a little quicker. So again, really helpful and important to, and it says, does say using exact values. So that means leave the square roots in there. Really important to just have that formula packet handy so you know which one you're using for whatever you're doing. Okay, I'm gonna open it up again because it got closed on me. That'll give me my unit circle right there. And again, formula packet 3.9. So we've got the enlargement, anti-clockwise or counterclockwise rotation of angle theta. If it's clockwise rotation, I don't actually like this. I think we should just cross that out and just plug in the negative value. So if it's clockwise rotation, just make the angle negative. Like this is what most of the rest of the world does. Don't don't have to complicate that. So our next one is going to be a clockwise rotation of pi over 3 about the origin. So that means the angle is negative pi over 3. So I'm going to use the same thing. I'm going to use negative pi over 3. Instead of having to have two different formulas. Just keep the one, and it's going to work out to be the same either way. Cosine of negative pi over 3. We'll go take a look at our unit circle since I got it open now. Oops, wrong one. Negative pi over 3 being the same as pi over 3, the cosine is still 1/2. The sine is negative square root of 3 over 2, and the negative square root of 3 over 2, which means the two negatives thus cancel and become positive. The sine negative square root of 3 over 2. So it's the same as the one that we did above it, but we just ended up just switching those two signs. And so all that did was switch which one is which. Now, this one wants it being rotated 150 degrees anti-clockwise or counterclockwise. So cosine 150, negative sine 150, sine 150, and cosine 150. Wants them in exact form, and it wants it to multiply it by that point. So I'll go back to my unit circle. 150, negative square root of 3 over 2 is cosine, sine is 1/2. So negative square root of 3 over 2, negative 1/2, sine being 1/2. Now I must multiply this by my point. So row 1 times column 1. Row 1 square root of 3 over 2 times 4 is 2 square root of 3 minus 3/2. Row 2 is 2 minus 3 square root 3 over 2. And that is our lovely transformation matrix. Oh, and they didn't give it an exact form. I'm a little disappointed in them. So, wait, I missed a negative here. There's a negative there. Highly disappointed in this book for that. But it's fine. Those are the same. Now it's time to talk about translations. Translations, moving from one place to the other without potentially. So write down these coordinates under the translated by the vector. So a transformation matrix will not be given for translations. You need to remember that a translation is just moving it. So this moves it down. So I'm going to put it on the graph, -2, 3, and I'm moving it down to over 2. So I'm moving it along that vector. So I just essentially add those. I get the point -4. Wait, that's not the correct vector. Back to this way, over to that way. That's the vector -2, 2. I get -4, 5. Essentially, I've just added my point and my vector. My x's, -2 plus 2 is -4, 3 plus 2 is 5. Make sure I did not screw anything. Yeah. And that's all they want you to do with these. So a triangle is translated first by the vector 2, 3, and then by 1, 1. Write down the coordinates of the vertices of the final image under these translations. Hence, find a single translation that would do this. So right to from -6 up 3. This would be A prime. And then 1, 1 is here. is a double prime. So essentially I'm going 3, 4 to combine the two transformations together. 1 over 3 up 4. Over 3 up 4. C prime, or C double prime. Over 3 up 4. B double prime. And we get our translated triangle. Same shape, different location. And to add them, you just literally add the vectors, add the x's, add the y's. Oh yeah, I guess those are the correct points. I really hadn't thought about what the points were. So, composite transformations. We're going to do the first one here. So, you can see multiple transformations happening to this triangle as it kind of spirals in towards the axis. And they've got a different one here. So if you play with sliders, you get different things. Notice that if you want it to spiral in, K does have to be less than 1. The rotation, depending on how much you're rotating, you can get different, very different ones. And N is how many transformations it's doing. Okay, that's what it's doing. So 0.32 is transformed by a matrix. In order in which transformations are applied matters. You keep multiplying them out. T1, so this is my point matrix. There. T1, T2, T3. They are going to apply from inside out. So 1, 2, 3. We're actually closest to the points working backwards. 0.32 is transformed to B by a transformation matrix that represents a horizontal stretch of the x-axis with scale factor 2. The point B then is transformed to C by a rotation matrix represented by 60 degrees. Write down a single transformation. So it's a horizontal stretch transformation, which can be represented by 2, 0, 0, 1. And we know that because we go look at our formula packet. And we see horizontal stretch K001, K being the scale factor of 2. My rotation of 60 degrees, again, we're going to go look at our formula packet. Rotation, 60 degrees anti-clockwise, it's positive 60. So I'm going to go cosine 60. I'm writing it up here because I'll write it next to the other one once I've simplified it. Sine 60, cosine 60, which gives me 1/2 negative square root of 3 over 2, positive square root of 3 over 2, 1/2. And so the first one has to be applied on the inside. And it asks me to put these together, so multiply them. So 2 times 1/2 is 1. That one goes away. Okay. Column 2, row 1, square root of 3. Row 1, column 2. Row 1 times column 2. negative square root of 3 over 2. Row 2 times column 1, 1/2. And my combined matrix should be this. So kind of key looking at and making sure we did everything right. I'm going to go back and double check that I read the problem correctly, but making sure I just use these transformations. 60 degrees anti-clockwise, yes. Wants them to 3 significant digits, so it wants me to round them. Oh, and so I'm supposed to multiply that by a point. Okay. Well, that's kind of lame. Equals 3 plus square root of 3. 3 square root of 3 minus 1. That's my point. My transformation matrix is right. My point, 3 plus square root of 3, that's correct. 3 square root of 3 minus 1, I'm sure that's right as well. And you could check any of these with the calculator. They apparently just multiplied with the calculator. We will pick up with this tomorrow and do some more composite transformations and then talk about how the area can be shown with any matrix transformation.